reinforcement learning has truly become a game changer for large language models, right? It's really pushing their reasoning abilities.
It's absolutely to new heights.
But for a long time, it almost felt like magic. We saw these incredible results, but how it actually enhances really complex reasoning, that was still a bit of a mystery.
Yeah, bit of a black box.
Well, today on AI Paper Podcasts, we're pulling back that curtain. We're diving into the paper Emergent Hierarchical Reasoning in LLMs through Reinforcement Learning by Haoju Wang and colleagues.
And what's really fascinating, what this paper reveals, is that RL isn't just randomly tweaking things. It's actually forging what they call an emergent reasoning hierarchy inside the model.
An emergent hierarchy. Okay, tell me more.
Think of it like a computational brain developing structure. High-level strategy becomes distinct from low-level execution. And it's surprisingly similar, they argue, to how we humans plan and carry out tasks.
Okay, so it's not just random improvement. This paper must have dug into the actual process then. What did they find?
Yeah, they identified this really interesting two-phase dynamic. First, the LLMs work on consolidating their low-level skills. Things like calculations, following syntax precisely, getting the basics right.
Nailing down the fundamentals.
Exactly. And only then do they make this decisive shift. They start exploring and mastering high-level strategic planning. And that shift, that's where the big reasoning gains really kick in.
Right. And I guess that shift means you need a different way to optimize the learning.
Precisely. Which is why they propose this algorithm, HICRA, pronounced HYCRA. It focuses the optimization pressure specifically on those high-impact strategic planning tokens.
Okay, so it's more targeted.
Much more. And it actually outperforms the existing methods quite significantly, partly because they also introduce this idea of semantic entropy as a better compass for measuring if the model is truly exploring different strategies, not just different words.
Super interesting. Okay, so for all of you tuning in, we're doing a deep dive today into emergent hierarchical reasoning in LLMs through reinforcement learning. This is really crucial stuff if you're building or researching the next wave of LLMs.
It really is. I mean, for those of us watching this space, RL's success in boosting reasoning, from the early work by Ouyang et al. To more recent stuff from Yuck et al., it's undeniable. We see the results.
Yeah, the empirical evidence is there.
But the why and the how, the actual learning dynamics have been pretty opaque. We've seen these puzzling things, sudden aha moments where performance jumps.
Right, or that length scaling thing where longer answers often seem to be better answers.
Exactly. And these really complex dynamics with token level entropy, it's been hard to fit all these pieces together with, our current understanding.
So this opacity, it basically led the authors to ask, what truly unlocks better reasoning in LLMs during RL training? And maybe more importantly for everyone listening, how can we use that knowledge to design, smarter, more efficient RL algorithms?
And their big hypothesis, the core idea, is that all those puzzles, the aha moments, length scaling, weird entropy stuff, they're actually all signs of one single coherent process.
Okay.
They argue RL is systematically building this emergent functional reasoning hierarchy within the LLM. It's not chaos, it's structured development.
And this is where that parallel to human thinking comes in, right?
Yeah.
Which is really cool.
Yeah, it's a compelling analogy. Think about how our brains work, right?
Oh.
We separate the high-level, deliberate, strategic planning deciding, okay, which theorem should I use for this math problem that's maybe prefrontal cortex stuff?
Right, the big picture thinking.
From the rapid, almost automatic execution of stuff we've already learned, like just doing an algebraic step. It's this functional separation that lets us handle complexity.
Makes sense. So how did they map that onto the LLMs?
They proposed this functional decomposition for how LLMs build solutions. First up, you have high-level planning tokens. These are the strategic moves, the ones that orchestrate the whole reasoning process. Think phrases like, we can use the fact that, or maybe deciding to branch, let's try a different approach, or even backtracking, but the problem mentions that.
Yeah.
They're the pivots, the decision points.
Got it. Like the conductor guiding the orchestra and the other part.
That's the low-level execution tokens.
Yeah.
These are the actual operational building blocks, the concrete steps.
Like the musicians playing the notes.
Exactly. Things like doing the arithmetic, substituting variables, just applying a formula you already decided to use. They're the workhorse tokens doing the step-by-step stuff.
Okay, but identifying which token is doing what? That sounds tricky, right? A token's role depends so much on context.
Totally. So they came up with this clever proxy method, strategic grams, or SGs. These aren't single tokens, but short sequences, maybe 3 to 5 tokens long, that act as a single semantic unit guiding the logical flow.
So like meaningful phrases that signal a strategic shift. How did they find these SGs?
They sampled a bunch of outputs from models during training, then used Gemini 2.5 with specific prompts to do an initial pass classifying these n-grams as strategic or not. And then, importantly, they manually reviewed and refined that list.
Okay, so a combination of automated classification and human oversight.
Right. And you can sort of hear it in the examples they pull out. When a model says, first, I need to minimize the expression. That's clearly planning. Or, let's look at the expression. Another planning step. Or even, but I'm not sure if that helps directly, alternatively. That's a classic strategic backtrace and redirection.
Yeah, you can really see the difference between that and just, say, outputting X and 5.
Exactly. So armed with this way to identify planning versus execution, they looked at the training process empirically, and they found this consistent two-phase dynamic across a whole range of models, QuIDM families, Llama 3.1, even multimodal models like MIMO-VL. It's a core finding.
Okay, let's break down those two phases. Phase 1, forging a reliable procedural engine. This sounds like getting the basics solid first, building that toolbox you mentioned.
That's spot on. And they tracked this using a couple of key metrics focused on those execution tokens. First, relative perplexity. Remember, lower perplexity means the model is more confident, less surprised by its own output. Right. What they saw was the perplexity for execution tokens just dropped really fast early in training, then flattened out. The model quickly got confident in doing the basic steps correctly.
Okay, rapid consolidation of the basics. What else?
Second, token-level entropy. This measures sort of the uncertainty or the exploration in the model's choices for the next token. And for these execution tokens, the entropy was consistently and significantly lower.
Meaning it wasn't exploring lots of different ways to do, say, addition, it just locked onto a reliable way.
Precisely. It reduced exploration of procedural alternatives once it found something that worked reliably.
So the big takeaway from phase 1 for us is this procedural consolidation isn't just happening, it's like a necessary first step. The model has to build that reliable engine for basic skills before it can effectively focus on higher level strategy. It's like that junior engineer needing to know the syntax before designing the system.
Absolutely. And once that procedural engine is reliable, the whole dynamic shifts. That brings us to phase 2. Steering skills with strategic planning. Now, the performance gains aren't really coming from doing the basics better.
They're coming from using those basics more intelligently, getting better at deciding what to do and how to approach the problem.
Exactly that. And the way they measured the strategic improvement is fascinating. They looked at the semantic entropy of strategic grams.
Okay, semantic entropy. So not just token diversity, but diversity of meaning or strategy.
Right. It quantifies the variety in the model's high-level plans. And what they found was a distinct, steady increase in the semantic entropy throughout phase 2. This is super important. The model isn't just finding one good strategy and sticking to it. It's actively expanding its playbook of different strategic approaches.
Ah, interesting. And what about the procedural side during this phase?
That's the contrast. The conditional entropy of the procedural grams stayed pretty stable. Once it knew how to execute reliably, it didn't need lots of different ways to do it. The action was all in diversifying the high-level plans.
So this strategic diversification, this increasing semantic entropy, it's not just some abstract metric. It actually connects directly to real improvements, right? Like longer reasoning chains and better accuracy.
Yes, absolutely. They show this rise in semantic diversity correlates directly with longer reasoning chains because more complex strategies often involve more steps and a sustained boost in overall accuracy. So takeaway 2 is pretty clear. Strategic exploration, measured by this semantic diversity, becomes the main frontier for learning once the basics are down.
And this whole two-phase framework, it suddenly makes those puzzling things like aha moments make sense.
It really does. An aha moment is likely just the model discovering and then reinforcing a powerful new strategy it hadn't used effectively before.
And length scaling.
That becomes almost expected. More sophisticated strategies naturally involve more planning, maybe exploring different cases, maybe backtracking, all of which leads to longer, more structured, and often better reasoning traces.
That ties things together nicely. It also highlights a big critique they make, right, about using just the aggregate token level entropy.
Yes, that's takeaway 3. Aggregate token entropy can be really misleading if you're trying to track exploration. Why? Because it's dominated by all those low-level execution tokens.
Right. And as the model gets better at those, their entropy goes down because it's more confident.
Exactly. So the overall average entropy gets dragged down, making it look like the model is exploring less, even when it might be intensely exploring new strategies at the higher level. It gives you a false signal.
Okay, so discovering this two-phase dynamic and the importance of strategic exploration, it really highlights a weakness in older RL methods.
It does. It exposes this core inefficiency. Algorithms like GRPO, which is a common baseline, tend to apply optimization pressure, the learning updates, pretty much agnostically across all tokens.
Not spreading the learning too thin.
Yeah, exactly. It dilutes the learning signal. They fail to really concentrate the learning where it starts to matter most in phase 2, which is at that emergent strategic bottleneck.
And this is where HRA, their proposed algorithm, comes in. You said HYCRA.
Yep, HIRA. It's designed specifically to fix this inefficiency by focusing the learning on those crucial planning tokens. It builds on the GRPO framework, so it's not a totally radical departure.
Okay, so how does it work? How does it focus the learning?
It cleverly modifies the advantage function. Now, the advantage function, put simply, is how RL figures out if doing a specific action at a certain time was better or worse than average. It assigns the credit or blame.
Got it. The reward signal gets distributed back.
Right. So HYCRA looks at a trajectory, identifies the planning tokens using those strategic rounds we talked about. If a token is identified as a planning token within a successful trajectory, HYCRA amplifies its advantage. Specifically, it adds a term. Alpha times the absolute value of the advantage, back to the original advantage.
So it gets a bigger reward signal, essentially.
A bigger positive signal if it led to success. And for non-planning tokens, the advantage just stays the same. That hyperparameter, alpha they used 0.2 in the experiments, controls how much amplification you get. It effectively boosts the credit for good strategic moves, and importantly, also dampens the penalties for unsuccessful strategic explorations, encouraging more strategic risk-taking.
Okay, so it's not just rewarding success more, it's also being a bit more forgiving of strategic failures to encourage exploration.
Precise.
And this reshapes the whole policy update, creating what they call an anisotropically stretched target distribution. That sounds technical, but what does it mean practically?
It just means the updated policy puts much more probability weight on those planning tokens, specifically within trajectories that led to high rewards.
So it creates this really nice virtuous cycle.
Exactly. You encourage more strategic exploration, which leads to faster discovery of good reasoning patterns, and then HYCRA strongly reinforces those patterns. It makes the whole process of learning how to plan much more efficient.
Okay, that makes intuitive sense.
Yeah.
But did they prove it works? What about the experiments?
Oh, yeah. They ran extensive experiments. They used models from several big families, Quen, Llama, even multimodal ones like MimoVL, both the base versions and the instruction-tuned ones.
And trained on relevant data, I assume.
Yep, standard stuff like DPO, DeepScaler for LLMs, VRL 39K for the vision language models.
And the tests. What benchmarks did they use?
A really comprehensive set for text reasoning, AMI, Math 500, AMC, Minerva, Olympiad, the usual suspects. For multimodal, MathVista, MathVision, MathVerse, MA, they compared HYCRA against the base models, GRPO, and also an entropy regularization baseline.
Okay, moment of truth.
Yeah.
How did DPO do?
The main results, shown in their tables 1 and 2, are pretty clear. HYCRA consistently and significantly outperforms GRPO and the other baselines. This holds across different models, different benchmarks, both text-only and multimodal.
Can you give an example, like how significant are the gains?
Sure. For instance, they reported a gain of over 5 percentage points on the AME 2024 benchmark for the Quen 3.4b Instruct model. And for the multimodal MimoVL Instruct, they saw a jump of 7 points on MathVista. Those are substantial improvements in these challenging domains.
Wow, okay, so the numbers really back up the claim that focusing on that strategic bottleneck pays off.
Empirically, yes. It seems to validate that core idea.
What about that error analysis? You mentioned RL correcting strategic faults.
Yeah, this part is super interesting too. Figure 4 in the paper. They manually checked where models were failing, then used GPT-4o to classify the errors. Was it a planning and strategy mistake or something else like a calculation error? Others?
And the pattern?
Very consistent. The main benefit of RL training, including with ALRA, was fixing those high-level strategic faults. It didn't necessarily make the models much better at basic calculations.
Really? So the bottleneck wasn't basic arithmetic?
For some base models, they found the rate of non-planning errors didn't even decrease. It strongly suggests the real limiting factor for complex reasoning is getting the plan right. A perfectly executed bad plan is still wrong.
That really drives home the point about the strategic bottleneck.
It does, and it further justifies HRA's targeted approach. They also compared HRA directly against GRPO and that entropy regularization baseline on the metric of semantic entropy.
Right, the measure of strategic diversity.
Exactly. HRA consistently achieved higher semantic entropy than GRPO, figure 5. It explored strategies more diversely. And crucially, that higher semantic entropy directly correlated with better validation accuracy. More strategic exploration led to better performance.
Okay, so HRA's targeted exploration works better than GRPO's more general approach.
Yeah.
What about just boosting all entropy, like the regularization baseline?
That's where it gets even clearer, figure 6. That baseline did increase overall token-level entropy, as expected, but it didn't translate into performance gains. Accuracy just kind of stagnated.
Why not? More diversity should be good, shouldn't it?
Because indiscriminately boosting diversity everywhere can just lead to, non-productive rambling or overly verbose ways of stating simple procedural steps. It adds noise without adding strategic value. HRA's targeted boost, specifically to the semantic diversity of planning, is what seems to make the difference.
Makes sense. Focus the exploration where it counts. But you mentioned HRA isn't a silver bullet. There's a limitation.
Right. There's an important caveat, figure 7. HRA's effectiveness seems to depend on the base model already having a reasonable foundation in procedural correctness.
So phase 1 needs to be somewhat successful first.
Kind of. If a model is still really bad at basic execution, forcing it to explore complex strategies with HRA can actually be counterproductive. It can lead to unstable learning. So HRA works best when the procedural engine is already somewhat functional.
Okay, that's a crucial detail for practical application. It fits the two-phase model perfectly, though.
It does. And it brings us back to the value of using semantic entropy as that compass for tracking strategic exploration, figure 8.
Yeah, you mentioned aggregate token entropy can collapse, and things like pass-it case saturate quickly, making them poor measures of ongoing learning.
Exactly. But semantic entropy, especially with HRA, often stays high and remains predictive of validation accuracy much longer into training. It shows there's still meaningful strategic exploration happening, which translates to better final performance, even in complex multimodal settings. It's just a much better diagnostic tool for that phase 2 learning.
Got it. One last nuance they explored was the difference between these functional planning tokens and just any token with high entropy, right?
Yes. A subtle but important point. Figures 9 and 10. They found that while most of the tokens they functionally defined as planning tokens did tend to have high entropy, they represent decision points after all.
The reverse wasn't true.
Exactly. Most high entropy tokens were not planning tokens. Many might just be points where there are multiple equally valid ways to phrase a simple execution step.
So just looking for high entropy isn't enough to find the strategic control points.
Right. It highlights that using entropy alone as a proxy for strategic function is limited. High entropy ensures sampling diversity, but it doesn't guarantee semantic or strategic importance. The functional role, identified via methods like strategic grams, seems more direct and reliable.
Okay, pulling this all together. It feels like we've moved from RL being a bit of a black box for reasoning to having a much clearer picture.
I think so.
We've uncovered this intelligent two-phase process. Build the reliable procedural engine first, then shift gears to explore and master high-level strategies.
Yeah, the hierarchy emerges through these phases.
And HYCRA leverages this insight by focusing learning on that strategic phase, leading to better performance, guided by this more informative metric of semantic entropy. Really does feel like a significant step towards, demystifying and actually engineering better LLM reasoning.
I agree. And this work, it really cracks open some exciting new directions for future research, pushing us to think differently about RL for language models.
Like what? What are the big open questions now?
Well, one provocative thought is, should we rethink the fundamental unit of action in RL for LMs? Maybe single tokens aren't the right level?
You mean moving to something higher level?
Perhaps. Should an action be more like a semantic concept or a distinct reasoning step like apply theorem X, or maybe even a whole phrasal unit like one of those strategic grams? Aligning the RL action space more closely with cognitive steps could be powerful.
Interesting. Like optimizing code blocks instead of individual assembly instructions.
Kind of, yeah. Another big area is designing dynamically adaptive hierarchical methods. Can we build algorithms that actually diagnose where the learning bottleneck is right now? Is it procedural skills or strategic planning?
And then shift the optimization pressure accordingly.
Exactly. Adaptively focus compute resources where they're most needed in real time. that could be incredibly efficient.
That would be amazing, like a truly smart tutor for the AI.
And finally, this work really motivates moving towards finer-grained, process-oriented rewards instead of just correct or incorrect at the very end.
You reward good steps along the way.
Yeah, maybe reward a brilliant strategic choice even if there's a minor slip-up in the execution later. Decoupling the evaluation of planning from execution could help the model learn both skills better.
That makes a lot of sense.
And of course, the big question is, does this emergent reasoning hierarchy concept generalize? Beyond math, does it apply to other complex tasks like code generation or maybe agentic tool use, or even generating long, coherent stories? Exploring that could unlock new optimization strategies across the board.